Hello, my name is Jared Skeens and welcome to the Zoom room. Today we're going to look at Pure Math 3 Integration Part 2, U Substitution, or it's called U Substitution. It can actually use other variables as well, but normally we'll use the variable U for a substitution. Now we're looking at different methods of integration or different ways to help us simplify an expression so that we can integrate it. So you learned in Pure Math 1 basic integration rules. And so what we need to do now is really work on your mental understanding of the options that you have. So I wrote up here again, I covered it in part 1. You'll thank me later. You really need to develop kind of a compartmentalization of your mind as to what you're looking for. If you don't know what you're looking for, it's going to be like a maze and you'll get frustrated and confused. So we really want to kind of compartmentalize our thinking here. So type recognition. And I have 6 things to keep in mind. Now, 3 of those will have a independent video for. This one is specifically focusing on U substitution. And it's kind of nice because it specifically says to substitute. Integration by parts will involve a product or a quotient. Okay, a product or a quotient. 2 terms, not like terms like algebraic with trig or logarithmic with trig, in a product or a quotient, and we'll use by parts. And differential equations already starts off with like a dy dx. So this one is pretty easy to identify, but it is also quite complicated itself. So these are the 3 main things that we're looking for. But in addition to those, we also have basic rules that we're going to be using throughout. Like once we've simplified down things, you still have to apply the basic rules. You still need to be able to look for this possibility, the top being the numerator being the derivative of the denominator. It might look algebraic, but it ends up being logarithmic. So we don't want to get caught off guard by that. Or if you have a fraction that doesn't follow number 2, it could be a partial fractions. So we need to keep that in mind. We learned partial fractions back in the first unit of Pure Math 3 in the further algebra section. So we've already learned it, but we need to also identify when we need to use that. So in addition to having these different possibilities, some problems are combined, meaning you could start with a substitution and then go into a partial fractions, or you could start with a substitution and go into a integration by parts, or you can even have an integration by parts where you have to do it 2 times in a row. So you really need to, at each step, not just at the first step, but at each step need to be able to reevaluate and consider your options before moving forward. So it's really important that you go through this and be familiar with your options. That way you don't get into that state of fear of, oh, I don't know something out there. Everything is here. You just need to be able to identify it. Now, before we get into the U substitution specifically, I want to show you the formula sheet. What do you have on paper in front of you? Okay, so in the formula sheet, I've opened it already up to the integration section. This is what you'll have when you take a Cambridge exam. There's more stuff here, like here's derivative up here. But you'll have this paper available to you. So when you get to these questions, have your formula sheet open so that you can quickly reference it. So what you have here at the top, these are the basic formulas. You already covered this is your algebraic formula. Here's your logarithmic formula. Here's your exponential formula. And here are your trigonometric formulas. And you learned all the way down to this one right here. These bottom two are not, I don't believe those are in our particular syllabus. So what we have is down to here. And then this one right here is actually your formula for integration by parts. We'll go over that again in the next video. And then here at the bottom of the integration section, before it gets into vectors, this is your logarithmic one with the derivative in the numerator over the function in the denominator. So the top is the derivative of the bottom, becomes ln function. So a lot of these things are in here. You don't have differential equations. Those are quite obvious. The substitution ones say to substitute and it gives you the substitution. But all of these are in here, but sometimes students fail to, look at this and kind of think through what they're doing. So make sure you take notes on this or take note of where this stuff is located. Okay, now, so type recognition, I'll keep going over this in each video to help you as well as in the problems to remind you so that you get more and more familiar with this. It's kind of a little bit of a mental map, sort of. It's not really a flow chart, but at least a listing. Also, don't forget, here is the basic guide when you're going through a question. You want to simplify, and your simplification will be done through these different ways, substitution or by parts or by partial fractions. So you'll want to simplify, then you integrate. So when you integrate, you're basically doing the basic rules of integration. And then at the end, you'll evaluate. So make sure you keep this 3-stage process in mind as you go as well. And for substitution specifically, what we're going to do is the problem is going to give you, usually uses the letter U, but not always. And it will say use U equals, and it will be in terms of X. In terms of X or theta, something like that. Could be in theta if it's trigonometry, but it'll be in terms of the variable of the original equation, and it will say substitute U equals something. Okay, so the second thing that we're going to do is we're going to take the du, the derivative of u, so that we can also substitute for the dx. So it's not just substituting for the x or the theta, but it's substituting for the dx or the d theta. So we're going to have to generate this one ourselves. Then as we start substituting the parts in, there might be something unaccounted for. And so we need to then go back and rearrange to find something that maybe hasn't been substituted yet. So this is going to be kind of the 3 levels here that will apply to make the substitution work. Then we'll need to change our bounds of integration from the original variable to the new variable. So if it was in terms of x and we substituted in u, then we need to change the bounds of integration from the x numbers into the u numbers for bounds of integration. So this is going to be what will help us with u substitution. So now I will set up for our first example. Okay, let's look at the first question here. Here we go. Says, let I equal the integral from 0 to 1 of x to the 5th over 1 plus x squared cubed dx. Using the substitution, u equals 1 plus x squared, show that I equals the integral from 1 to 2 of u minus 1 squared over 2u cubed du. Then find the exact value of I. In other words, go ahead and integrate it and calculate it out. Keep it in exact value form. So let's go back to the board. And this is what basically you want to do. First of all, the problem identified us to use substitution. So here's the original equation. This integral equals, or I assume it stands for this integration. It's going to be the integral of from 0 to 1 of x to the 5th over 1 plus x squared cubed dx. Says use u equals 1 plus x squared. So this is our substitution part that's given. And we need to show that it can become this integral here. So we're changing from x's into u's, including our bounds of integration. So how do we do that? First thing you do is you start with what's given. U equals 1 plus x squared. Then the very next thing you should do, don't even substitute it in yet. Write the given and immediately write the derivative of the given. So the derivative becomes du equals the derivative of 1 is 0 and the derivative of x squared is 2x dx. Make sure you keep track of the differentials. Okay, so du equals 2x dx. These are our two main things. We have to get rid of the x and we have to get rid of the dx. So we have a given substitution and immediately we take the derivative so that we can identify the dx. Now, when you look at what's up here, there's going to be an obvious part of the substitution. The 1 plus x squared should plug in directly. Usually the given statement plugs in directly somewhere. So here we see the 1 plus x squared, 1 plus x squared. So we can just plug it in directly and now we get u cubed. Don't forget the exponent on the outside here. It's being cubed and 1 plus x squared is our u, so we get u cubed. So that's the obvious part. Now we want to look at the dx part, but we want to know what else is attached to the dx, and that's where this helps. So the du equals 2x dx. Well, here's our dx, but we need an x with it. The 2 we can work with if we don't find a 2. So the x dx, well, there's 5 x's up here, not 5x, but x to the 5th power, 5 powers of x. So that means we can change it into an x to the 4th power times x. Now we see our x dx. We don't have the 2, so we can just divide the 2 to the other side. So what we do have is the x dx, that's the important part. So we've taken one of the x's away from the 5 power, reduced it to 4th power. So we have our x dx, but we need to figure out what its substitution value is. We need to divide by 2, so our x dx becomes 1/2 du. So the 2 in the denominator shows up right here. So that we put the 2 in. So here's the 2 and the du. So the 2 in the denominator and the du is right there, replaces the x dx. So the u cubed came from the original substitution, and then the 2 in the denominator and the du came from the differential. Now, we still have this x to the 4th. This is the unaccounted for. Okay, so we did the original, the given substitution. We also figured out the differential part. Now we need to rearrange for what's unaccounted for. We haven't accounted for the x to the 4th yet. So if we look, x to the 4th is the same thing as x squared squared. And we have an x squared. So if we rearrange for our x squared, we get u minus 1. So now we can stick u minus 1 in for the x squared, and it needs squared again to have that fourth power total there. Now we have everything in terms of u. Now we need to do the bounds of integration. I usually leave the bounds of integration. You can do it first. It doesn't really matter when you do it. So here's our u. So what I do is we're going to evaluate it when our x is 0 and 1. And what does that give us? So when we plug in a 0, because this is for the variable x, we get 0 plus 1 is 1. So when we plug in 0, we get a 1. And when we plug in a 1, 1 squared is 1 plus 1 is a 2. So what we're doing is we're changing our x boundaries into u boundaries. Bounds of integration for variable u. So we want to use 2 and 1. So we put 2 and 1. Those are our new bounds of integration. And we have now done the substitution part of the problem. Okay. Now, I'm going to keep this part, but I need to erase some things to make room for the second part of the question. Okay, let's look at the second part of that question again just to see what it said. It says, hence, find the exact value, so no decimals. You have to keep everything in its algebraic form without using calculator. And find the exact value of I, meaning go ahead and do the integral is what that's saying. So when we come back, we end up with this. This is where we ended up after the u substitution. Remember, the u substitution is supposed to simplify something complicated by doing these substitutions and changing it into something a little simpler. But when we look at this, it's still not really simplified enough. We did get to the place where it asked us to get to in the show problem. But before we can integrate, we actually need to do a little bit more. We still have this kind of complicated fraction here. And if you look at our options, you're complicated for fractions, if you remember from their recognition things, the first one was the top is the derivative of the bottom. Well, that's not the case. Or partial fractions. Well, if you look at partial fractions, the top exponent is a u squared and the bottom exponent is a u cubed. It's not an improper fraction, and you only have one factor in the denominator. Usually with partial fractions, it's either going to be an improper fraction or you're going to have multiple factors in the denominator. So both of our identifications for fractions don't work, meaning there's probably something just basic algebraic rearrangement that we can do. This on top is a square. Let's just multiply it out, expand it. So we expand this x or u minus 1 squared, and we get u squared minus 2u plus 1 with the one denominator here. Now remember, division distributes to add and subtract just like multiplication does. We're very used to distributing multiplication through a parenthesis. Well, you can also distribute a division through the numerator. Same way, same thing. So what we get is u squared over 2u cubed minus 2u over 2u cubed plus 1 over 2u cubed. And because we want to integrate, and they are our basic rules or exponent rules, we're going to bring those all upstairs. So this cancels and becomes 1 over 2u. This one becomes 1 over u squared. This one is already simplified, but we want to move them to the numerator. So we bring the u up. So it's 1/2 u to the negative 1. We bring the u squared up minus u to the negative 2 plus 1/2 u to the negative 3. So notice between here and here, all of this is just algebraic simplification. You didn't have anything in that identification list to help you. So if there's nothing in that identification list to help you, it means you need to algebraically rearrange it so that it's in a simpler form. And so we just divided it, or we expanded the binomial on top. Then we distributed the denominator through and simplified it, and then brought each one to the numerator with a negative exponent. Now we can follow the basic math rules, which was our very first part in our identification. Now we can recognize to use the formula from the formula sheet. This one, it looks algebraic, but remember when you have that -1 exponent, it's actually your logarithm. And the way you can tell is, remember your formula for integration is to add 1 and divide by the number. Well, if you add 1 to -1, you get 0, and you can't divide by 0. So don't forget your 1 over x is actually ln x, in this case u. So we get 1/2 ln u, we use the absolute value signs. Then for this one, this is algebraic, so we add 1, we get -1, divide by -1 now gives us a positive, and -2 plus 1 is a -1, which is the same thing as 1 over u. So we get u to the -1, I just made it 1 over u, the negatives cancel. Here we add 1, that gives us -2, which means it goes in the denominator. Divide by -2 means you're multiplying the 2 here by -2, which becomes a -4 in the denominator. Okay, so this part is the mechanics. This is the integrate part. Everything up to this point had been the simplify part. Now we're in the actual integrate part, and you just need to be very careful with your mechanics, thinking through your basic rules, following, if it's algebraic, following that add 1, divide by the number, add 1, divide by the number, and make sure you're very careful in your executing of those basic integral formulas. Then when we get to the end, we're going to evaluate it for our bounds of integration from 1 to 2. And remember that you do the top minus the bottom. Top minus the bottom. So we plug in our 2. So it gives us a 1/2 ln 2 plus 1/2 minus 1/16. 2 squared is 4 times 4 is 16. That is the top one minus the bottom. So you plug in a 1. You get 1/2 ln 1 plus 1 over 1 is just 1. And 1 squared times 4 is 4. So you get a -1/4. Then you simplify those. So we get 1/2 ln of 2. 1/2 minus 1/16 is a positive 7/16. Over here, ln 1 is 0. If you did it on your calculator, you would get 0. But you need to remember, how do you get a 1? Anything to the 0 power is 1. So when you're dealing with 1 or any log with 1, it's going to be 0. So 0 times 1/2 is 0. So you just get the 1 minus 1/4, which is 3/4. Then our 1/2 ln 2, there's really not much we can do with that for the logarithm. And then we get 7/16 minus 3/4 is a -5/16. You could have taken the 1/2 and moved it up as the exponent, which would give you a ln of √2 as possible. So you could have a ln √2 minus 5/16. That one would also be correct, but this is the form that they have in the mark scheme. So whether you move this up as the exponent or not doesn't really matter. This logarithm can't really simplify any further, and the numeric part simplifies to -5/16. This is the exact value. Don't try to do anything more to it. And need to turn this here a little bit so that you can see all of it there. And this then is the answer that they're looking for. So notice we have simplify, which was the first part of the problem, even into the second part of the problem. Integrate, that's your mechanics, and then evaluate, plugging in the numbers and working it out. So this is your 3-stage process: simplify, integrate, evaluate. In order to simplify, that's where your recognition types come in. How do I simplify? Do I simplify by substitution? Do I simplify by parts? Do I simplify by partial fractions? You know, how do you get it to simplify so that you can integrate? You need to be able to recognize when your integration rules are able to be applied and when they're not. So that's the trick to these questions. Let me set up for the next one. Okay, let's go to our second problem. And we see that we have this graph and we have this area under the graph. The diagram shows the curve y equals 5 sine squared x cosine cubed x from the interval from 0 to pi halves. It has a maximum point and a shaded region bounded by the curve in the x-axis. So the first part says to find the x-coordinate of m. Now this has to do with stationary points. We've already covered that previously, so I'm not going to focus on that part. What we want to focus on is the second part. It says using the substitution u equals sine x and showing all necessarily work, find the exact area of R. So here we have a u substitution to do and we're finding area. And I do want to point out this first part of the problem was a stationary point, which means you are doing the derivative. Now we're doing the integral, so be careful that you don't get confused which direction you're going. In part 1, you're doing derivatives. In part 2, you're doing integration. So just be careful with your mechanics. And now let's go back to the board. Okay, here was the original equation. By the way, don't forget to set your calculator to radians because we are dealing with trigonometry. And if you use your calculator, which really shouldn't have to, but if you did use your calculator, you want to make sure you're in radian mode. It says to use u equals sine x. This is our substitution, u equals sine x. Find the exact area, and remember, integrating is our way of finding area. So simplify, integrate, evaluate. First, we're going to simplify by doing the substitution, then we'll integrate, and then we'll evaluate. So here is basically the same equation, but now set up for integration. You need to add the dx. Don't forget to add the dx yourself. Sometimes they give this to you as show. In this case, they don't give it to you as a show. You have to get it from the original equation. You need to add the dx. That's an important part for your substitution. Anytime you're integrating, you should have that differential at the end. Also, our bounds of integration came from the graph. If you remember, the graph went from 0 to pi halves. So that's where the bounds of integration come from. You just go back and look at your diagram to see what section the area is being taken of. And you have your equation and your differential. So those are the important elements. Now we move into our substitution, how to carry out the substitution. First, you write the given statement, u equals sine x. If you want to, you can go ahead and change your bounds of integration. Our bounds of integration, oops, sorry, I put this at pi, it's supposed to be pi halves. There we go, from 0 to pi halves. So when you plug in a 0, sine of 0 is 0. You should already know that, but if you need your calculator, do it. Also, sine of pi halves, which is 90, is 1. Again, you should already know that, but you can use the calculator if you need to. So our bounds of 0 to pi halves become 0 to 1 for the u bounds of integration. The other thing that you want to do is you want to do your differential or derivative. So du equals the derivative of sine is cosine, and don't forget the differential dx. So now we look for the obvious part. The obvious part is right here. Sine x becomes u, so that part becomes the u squared. The 5 has no problem. There's no substitution for that. And we need a cosine x dx. Well, here 3 powers or 3 factors of cosine x. So we take out one of those, that leaves us with a cosine squared that is unaccounted for. The cosine dx, or the cosine x dx, becomes the du. So all of that is in the du differential. So we've got this accounted for, we've got that accounted for. Now this third part is we need a cosine squared x. You can rearrange if it's like algebraic, but in this case it's trigonometric. So the rearranging basically means to use an identity. So cosine squared x is 1 minus sine squared x. We now have it in terms of something that we can substitute. And so that becomes 1 minus u squared. So we see this becoming right here. So we get our new bounds of integration, 0 to 1. 5, our u squared came from the direct obvious substitution there. Then our 1 minus u squared and the du. That is all part of the simplify. Actually, we can simplify one more because right now we have a product. Now, you did learn the product rule, but the product rule is usually when you're multiplying unlike terms, like an algebraic with a logarithmic term. If you're doing multiplication of algebra, you can use the product rule, but you don't need to. You can just distribute the 5u squared, and you get 5u squared minus 5u to the 4th. So it's probably a little bit easier to do it this way than with the product rule. And now it's just your basic algebraic rules. So don't forget, you add 1 and you divide by that number. So you end up with 5/3 u cubed. Here you add 1, divide by that number, and you get minus u to the 5th. Okay. So just basic integration there. We're in the integrate part. Now we move to the evaluate part. We're going to evaluate it over our bounds of integration from 0 to 1. Remember, it's top minus the bottom. Plug that into 1. 1 cubed is 1 times 5/3 is 5/3. 1 to the 5th is still 1. So 5/3 minus 1 is the top part. Minus, plug in 0 and everything cancels out to 0. So 5/3 minus 1 is 2/3. 2/3 is our answer for this particular question. This one was pretty straightforward, but you did have to do a little bit of rearranging or identities with the trigonometric part in order to get it to simplify or to change it over into the u substitution values. Okay, we'll look at one more substitution example for this video. Okay, let's look at the last problem for this video. Here we have, this is from Summer 18, paper 31, number 5. Let I equals the integral from 1/4 to 3/4 of the square root of, and notice the parentheses here. In Cambridge, they don't put a roof on their radical. So the parenthesis means all of this is under the radical. And you have x divided by 1 minus x, and then dx is actually on the outside of the radical. Using the substitution, x equals cosine squared theta, show that I equals the integral from pi6 to pi3 to cosine squared theta d theta. So this time they're not using u, they're changing from x into theta. So let's go to the board. The concept is still the same. We're starting with this, and we want to end up with this down here. So the first thing that we want, and here it gave us the substitution and what to show. So the first thing is we state the given, x equals cosine squared theta. I went ahead and did the bounds of integration, plugging in 1/4 and 3/4. But remember, this represents x, not the theta. So we need to plug that into the x. Also notice that we had pi's here. So again, make sure that your calculator is in radian mode, but you're not going to want to use your calculators because we want exact answers here, not decimals. So if you plug in 1/4 into x, then you have to square root 1/4. We need to get in terms of theta. So we're actually plugging the 1/4 in over here. This is a little backwards from our previous examples. So 1/4 square root is 1/2. Where does cosine equal 1/2? Use your special triangle to help you so that you're not getting into decimals on your calculator. So where do you get a 1/2 with an adjacent over hypotenuse? And that's from 60. 60 in radians is pi thirds. Remember, pi is 180. So 180 divided by 3 is 60. So pi thirds is our value for that. When we plug in 3/4 and we square root that, we get root 3 over 2. So for a root 3 over 2, you're coming up from the 30 degrees, adjacent over hypotenuse. So it's 30 degrees, which is pi 6. 180 divided by 6 is 30. So our bounds of integration are pi 6 and pi thirds. And notice I put a question mark. Why did I put a question mark? Well, normally these bounds of integration are supposed to go from the smallest to the largest. The smaller one should be on the bottom, the larger one should be on top. When we converted our bounds of integration from x to theta, now we end up with the smaller one on top and the larger one on the bottom. So we need to keep that in mind. We don't want it to stay that way, but we're going to leave it that way for now. Then after our given statement, we need to do the derivative. So the derivative is dx equals, multiply the exponent to the front, we get 2 cosine x. The derivative of the trig function is a negative sine theta d theta. So first exponent, that puts the 2 cosine theta. Then the trig function is a negative sine theta. Then the derivative of the argument is the d theta. So all of this is the dx. Well, let's make the substitutions that we can see. Here's x and here's x. So now we have a root of cosine squared theta over 1 minus cosine squared theta. Those are in the radical. Outside the radical was the dx, and we replace it with this long trigonometric expression here, minus 2. This isn't a subtraction sign, it's a times a negative. So don't confuse that. Make sure you have it in parentheses, it's multiplying. And we put in our new bounds of integration, although they're upside down right now. So we can recognize that this 1 minus cosine squared theta is an identity. And be careful, don't cancel the sine theta with the sine squared theta yet. This is a multiply, this is a radical. Radicals come before multiply. Make sure you follow your orders of operation. Radicals come first. So the square root of cosine squared over sine squared is cosine over sine. Now division and multiplication are opposites. Now you can cancel out the sine thetas, and we end up with our 2 cosine theta squared and our d theta. Now what happened to the negative sign? This negative sign, when you have a negative that is multiplying in your integral at some point, that can be taken out, and that is what flips your bounds of integration back. So in other words, a negative a over b, or a to b, this is how you normally write an integral from a to b. A negative of a to b equals b to a. So if you're wanting to flip your bounds of integration so that the smaller's on the bottom and the larger's on top, look for that negative sign. That negative sign is what allows you to do it, and then you can get rid of the negative. So this negative right here is what flips our bounds of integration, and the negative goes away. So that's how you can take care of that. But you need to be looking and thinking about larger and smaller. It's a little bit more difficult to see when you're using radians as it is when you're using regular numbers. So that's how we get to our show part, is we've done all of these things. Again, follow the correct order of operations. Radicals before multiply, so don't cancel until after you've done the radical. And we get what we were looking for. Okay, now let me set up for the second part of the question. Okay, now the second part of the question says to find the exact value of I. So now we need to integrate it. So at this point, you might be sighing or breathe a sigh of relief that we've shown that we got this 2 cosine theta d theta, and you think that you're ready to integrate. But there's a problem. If you go to your formula sheet and you look at your basic trig integration formulas, there's nothing with cosine squared. There's cosine. You can integrate cosine, but you can't integrate cosine squared. And you might think of your first identity, oh, that's a Pythagorean identity, 1 minus sine squared, but you still end up with a trigonometry squared. There's no integration for sine squared in our formula either. So this is where people can start to panic and say, what do I do? Or they just try to do exponent rules, add 1, divide by the number, and you end up with a mess. So don't do that. If it's not in your basic formula, then that means you need to use an identity. So let's go to our identity or our formula sheet really quickly. Notice down here in the integrals section, there's no cosine squared. There's a secant squared. There's a cosine. There's no cosine squared. So don't try to push something that is not there. Instead, we go back up here to our formula, to our identities, and what we're looking for, it's not the argument that's the problem. The problem is the exponent. How can we get out of our trigonometry having, our trigonometric function having that squared power? So let's look for all the places where there's a cosine squared. Well, here's one right here. Cosine squared, we already know, equals 1 minus sine squared, but we still have the power up there. If we come down here, we see cosine squared, we see cosine squared, but is it possible to get out of the cosine squared? If we use this one, here's cosine squared, but it still has a sine squared to it. Now, right here, this is the one that you're looking for. Notice 2 cosine squared A minus 1 is equal to cosine 2A. So we have our cosine squared, and there's no other power on the trig function. We can reduce it down to cosine 2A. Don't worry about the argument. The argument's not the problem. The problem is the exponent. Okay, let's go back to the board. So what we have here is we looked up 2 cosine squared theta minus 1 is equal to cosine 2 theta. Well, we just need the 2 cosine squared theta part, and we don't want an exponent on the other side. So we add 1 to the other side, and so we can replace that with cosine 2 theta plus 1. So we still, even though we already did the substitution method, we still have to do a little bit of simplifying before we can integrate. Your integration should be carrying out those basic formulas that you have in your worksheet, or basically the basic formulas. So we have the integral of pi thirds to pi sixths, now of cosine 2 theta plus 1 d theta. Now we can integrate. The integral of cosine is sine, and then don't forget, because this is expanded form, your argument is expanded. So you need to divide by the derivative of the argument. So the integral of cosine is sine, so you get sine 2 theta. The derivative of the argument is 2. So you have, because we're integrating, you have to divide by that number. So you get 1/2 sine 2 theta. If you're not sure, just derive it and go backwards. So the derivative of sine is cosine, multiply by 2, cancels the 1/2, and you're right back to the start. So do that forwards and backwards just to make sure your mechanics are correct. Then on this one, don't forget you are integrating, not deriving. When you derive a constant, it becomes 0. But when you're integrating a constant, it becomes your variable. So the integral of 1 is theta. So this one right here, a lot of students forget that. They think they're deriving and they just cancel it out. So don't forget that becomes a theta. And then now we're into the evaluate part. And so we're evaluating from pi thirds to pi 6. And because we're doing exact values and we're using trigonometry, I pulled up our special triangle. So pi thirds is plugged in here. And so you get 2 pi thirds. 2 pi thirds is 120, which means you have a 60-degree in the second quadrant. Okay, so that means you have your 1, 2, and root 3. And it would be 60 degree is your root 3 over 2, but it's in the second quadrant. Sine is positive in the second quadrant. So this is just root 3 over 2, a positive root 3 over 2, because it's in the second quadrant from a 60-degree angle in the second quadrant, root opposite over hypotenuse. Then we put the pi over 3 in for the theta, minus, and then we put the pi 6 in. The pi 6 makes 2 pi 6, which reduces to pi thirds, which is a 60-degree in the first quadrant, which is still positive, and it's still root 3 over 2. So we have the 1/2 times root 3 over 2 again. So this one was in the second quadrant, this one is in first quadrant, but they're both positive with the same ratio. And then we put the pi 6 in for the theta. So this becomes root 3 over 4 plus pi thirds. Distribute your negative, a negative root 3 over 4 minus, distribute, make sure you're distributing that negative, minus pi 6. The root 3 over 4's cancel. So pi thirds is the same thing as 2 pi 6 minus 1 pi 6 is just pi 6. So pi 6 is our answer to that integral problem. So here we went through 3 examples, and hopefully you see now these are multi-step problems, and you really need to structure your thinking so that you can successfully achieve these Cambridge questions. As always, thank you for joining me in the Zoom room, and hope to see you again next time.